Good afternoon. So, this will now be our 15th lecture, and so what our plans are for this lecture is to continue our discussion on the standard array decoder, and in the last lecture we were focused on using the standard array decoder or the syndrome decoder for the purposes of decoding. Our purpose this time, however, is different. Here we are interested in actually trying to see what is the performance in terms of probability of error of the standard array decoder. So, we would like to know, for example, what is the code word error probability, etc. So, I am going to give the title of this lecture as performance analysis of the standard array decoder, right. Now, so as a recap, we introduced the standard array, defined the syndrome, and set up the procedure of standard array decoding. So, we laid down the steps involved in carrying out standard array decoding, right. Now, towards the end of the last lecture, and so again let me see if I can actually copy that. So, what I would like to do is copy this page here, and let us paste that here. Okay. So, we want to use the standard array for carrying out performance analysis, and the goal in performance analysis is to determine the probability of error, and there are different probabilities of error that come into play, and we will begin with by focusing on the probability of code word error. Now, the first thing is, the first point to note is lemma 1. The received vector and the error pattern E belong to the same coset of the code, and hence share the same the same syndrome. And the proof is obvious, so I just thought it would be nice to draw attention to it. The proof is because y is c plus e, it is clear that they that y and e belong to the same coset. Okay. Therefore, y e belong to the same coset of the code. Now, the part about sharing the syndrome, so h times y is equal to h times c plus e, which is h times e, and hence y and e share the same syndrome. Now, let us go back to the standard array and say, and now let us view the elements of the standard array. Now, earlier we were viewing them as received vectors, and we were saying, supposing this was the received vector, what would happen, and so on. But this time we are going to change our view. We are going to look at the same table, but now we are going to treat each entry in the table as if it was an error pattern. So, for example, supposing going down to this table here, let us say that the error pattern, for instance, was 0 1 1 1, and let me circle, let me pick a different one, since I believe I picked that one. So, let us say that the error pattern is 1 1 0 1, and I am going to encircle that in blue. Okay. So, let us say that that was your true error pattern, which is the true error pattern or vector. Now, what is the receiver going to do? It is going to compute the syndrome of the received vector, but the syndrome of the received vector is the same as the syndrome of the error vector, which is this. So, in this case, the syndrome that is going to be computed is this, and once it is given the syndrome, it is going to use table lookup and it is going to jump to the coset leader. So, it is going to jump to this coset leader. Now, given this coset leader and given this received vector, the algorithm says that you take this coset leader and add it to the received vector. Okay. So, let us see what that does. So, this we finished our theorem. So, suppose E to be the true error pattern. So, we compute, the decoder computes the decoder computes HY, which is the same as HE, and that is your syndrome. And then next, let E hat be the coset leader associated to syndrome S. Then the decoder computes computes Y plus E hat, which is C plus E plus E hat. Okay. So, let us call this E tilde, and I am going to call this the residual error pattern. So, what this is actually saying is that the combination of the channel and the decoder result in a residual error pattern, which is really the sum of the true error pattern and the coset leader, because the coset leader is really your guess at the error pattern. Now, if it happens that you guessed correctly, then the error vector and the coset leader will cancel each other out, so that your residual error vector is 0. but that may not happen always. Okay. So, in which case you would have a non-zero residual error pattern. And now what I want to identify, what I want to do is identify in the standard array the residual error pattern. Okay. So, here getting back to our example, I said let this be our true error pattern, and then here is your coset leader, and we also agreed that we would actually call this coset leader, we would call this E hat. And now what would the decoder do? It would actually compute y plus E hat, and in the process create a residual error pattern, which is the sum of E hat plus E. So, that means the residual error pattern in this particular case is the sum of this plus this. But the way this table is set up, that sum is exactly here at the head of this. So, that means that the residual error pattern is in fact nothing but this. So, this is E tilde. And now, so let us say that this is the, let us point out that this is the residual error vector, which means the residual after decoding. So, now you have a very nice way of thinking about what happens when you employ standard array decoding. The error pattern can be any entry in the table, and the residual error vector is simply the vector that is at the head of the column corresponding to the true error pattern. Okay. So, let us go down to the table again and we will look at some examples. So, if for example 1101 was in fact the true error pattern, the residual error vector is 1111. If it was 1000, the residual error vector is 1010. Alright. So, let us make a note of that. It follows then that in the standard array the residual error vector E tilde is the vector in the table at the head of the column to which E belongs. And just to cement this concept, I thought we might draw a picture like this. So, the idea is that you have the code word and you have the true error vector E. This is followed by the syndrome computer, by the syndrome computation. So, you compute H times Y and what you get is S. Then you have table lookup. So, standard array table lookup, and what comes out of this is E hat, which is the coset leader. And then what you do is you take the output of this and this and you add the two. You add the two, and now this is your C hat, your decoded code word. But what is interesting is that since you have estimated the error pattern, you can also write, you can also identify that down here. Okay. So, in some sense the combination of channel and the decoder create the residual error pattern. So, it is just a way of thinking about this. So, getting back to this table now. So, in terms of performance of error, supposing I were to ask you, okay, which error patterns is the code able to correct, okay, and you look down at this table and say, look, if in fact I am able to correct an error pattern, then the residual error vector must actually be 0. So, the only error patterns that I can in fact correct are those for which the residue is 0. So, I look in this table and I say, well, but I know that the residual error vector is always the vector at the head of the column. So, I look at the table, let us go down to the table please, and then you see that in fact the only place where the residual error vector is 0 is in fact at the head of the first column. So, the only error patterns that the code is able to correct are precisely the coset leaders. Okay. These are precisely the, okay. So, let us put that down. It follows that the only error patterns that the code is able to correct are precisely the error patterns corresponding to the coset leaders. Okay. Now, all right. So, then you can immediately write down also the probability of decoding error, because you incur an error precisely when the error pattern is not one of the coset leaders. So, let us do that. So, let me see if I can select a section of this table. If it does not work, I will copy the whole table and I will repeat it. Let us see if I can copy here. Okay, very good. So, I am able to copy a section of the table, and I guess we do not need these lines. So, hence the probability of code word error is given by and I am going to write CWE to denote the probability of code word error is 1 minus the probability of no error, okay, and no error happens precisely when the error pattern is one of the coset leaders. So, I can write this as 1 minus epsilon to the 4 plus 1 minus epsilon cubed epsilon. Actually, let me just rewrite that slightly. It was correct, but I really should write plus 2 into 1 minus epsilon cubed into epsilon plus 1 minus epsilon squared into epsilon squared. So, in other words, what I am looking at is I am looking at these coset leaders here, and the probability of this coset leader being an error pattern is 1 minus epsilon to the 4 on the binary symmetric channels, because we assume that the errors are independent from bit to bit or from symbol to symbol. And again here if you look at the coset leaders, then the second and third coset leaders both have Hamming weight 1. So, their corresponding probabilities are given by this, and since there are 2 of them, I multiply by 2, and this is the last term. So, this is the probability of bit error, and of course, this whole thing is small because this thing is hopefully close to 1 when epsilon is small. So, now we have the probability of code word error, but it is interesting that you can also use it to actually determine other error probabilities as well. So, let us do that, and again I am going to select this thing here. So, I am going to select the table again, let us copy it and put it down here. Okay. Now, this time what I want to do is with the same standard array, let us say that I am interested in finding out what is the probability that the first message bit is an error, and I am just going to do this as an example, but from this it will become clear that you can find out any kind of message bit error that you are interested in. Okay. Now, recall, so these are your code words, right. So, these are your code words in the code. So, this is your code. I am going to write down form another row on top which contains the underlying message symbols. Okay. So, these are now we agreed that M transpose G is C transpose is the equation that actually describes how a code word is generated, right. So, what I want to do is I want to put down in this table the corresponding message vectors transpose, but this being a systematic code, the message symbols are explicitly present in the code as the first 2 symbols. So, for example, the message symbols here, maybe let me use blue, are 0 0, the first 2 symbols, 1 0 from here, 0 1 and 1 1. Now, if the residual error vector is always the code word at the top of the column, the residual error pattern as far as the message symbols is concerned are precisely these. So, you can also view these as residual message error patterns. Okay. So, what that means is that for example, if E, let us say E was 1 0 0 1, then E hat would be 0 0 1 1. Therefore, E tilde would be 1 0 0 1 plus 0 0 1 1, which would be 1 0 1 0. Okay. And you will find that pattern over here. This is now, as discussed earlier, this is your residual error vector. But now we are interested in what is the residual error insofar as the message bits are concerned. So, you can see from here that since you recover the message symbols by stripping the first 2 symbols of the code, it is clear from this that M1 is decoded erroneously M2 is decoded correctly. The reason being that the 0 here, that this symbol here corresponds to the first message symbol, this one corresponds to M2. Right. Now, just in case any further explanation is needed, do not forget that your C hat is C plus E plus E hat, which is C plus E tilde. Okay. So, that is the reason why I am saying that the first two message symbols, whether they are correct or not is determined by the first two symbols in E hat, E tilde, because of this. So, once you have this, now if I go back to this and I ask you what is the probability that let us say that the first message bit is an error, but not the second. Okay, if I want to know what is the probability that M1 is an error, but not M2, then you can actually see that the only error patterns for which that is true are precisely those which correspond to these columns, because here there is no error in either message symbol, here there is no error in the first, there is an error in the second, here there is an error in both. So, this is precisely the set of all error patterns for which the first error, the first message symbol is decoded erroneously and the second is not. Okay. So, so now let me just again do this, select this. It follows and I am going to circle this column because this is the key here. It follows that the probability that M1 erroneously decoded while M2 is correctly decoded is given by, and I am going to write this computation here. So, the computation is just corresponds to this, it is equal to, and I just sum the probabilities that the vectors in this column are the error vectors. So, you can see that two of them, one of them has Hamming weight 1, 2 have Hamming weight 2 and this. So, you can see that therefore, it is 1 minus epsilon cubed epsilon, this is for the single error vector, plus 2 1 minus epsilon squared plus the case when you have 3, you have plus 1 minus epsilon into epsilon cubed. So, this is the probability that the first message symbol is decoded correctly, whereas the second is decoded incorrectly, whereas the second is decoded correctly. Now, one thought that might be crossing your mind is, okay, that is fine because this is a systematic code. What if it is not systematic? Can I still do this? And if you think about it, yes, you can. The only thing is that the only advantage of a systematic code really is that when you actually set up a table like this. So, let us go down here. When you set up a table where you have the standard array and then you list the corresponding message symbols. In the case of the standard array, the message symbols are apparent from the code word. You can just simply pick them out as being the the first two symbols. Now, if this was not systematic, then you have to work a little bit harder, because you have to go to the generator matrix and figure out what is the underlying message vector corresponding to these code words, and then you can do exactly what we did. So and then you can exactly repeat what we did here. So, systematic or not, you can use the standard array decoder to compute whatever expression you need relating to bit error probabilities. Okay, so it's quite powerful in that sense. All right. So I think with this, what I'd actually like to do is I want to move on to the next topic, but perhaps I think just looking at my notes here, I think I should emphasize one point before we complete this section, conclude this section. Note the residual error pattern E tilde is independent of the transmitted code word. And this is what enables this analysis to be carried out. Okay. Perhaps no exclamation mark, it is more a note of a reminder note. Okay, so let us go back here. So, when we did the analysis here and I started saying, well, supposing this is the error pattern, then this will be your coset leader and this will be your residual error pattern. I never actually mentioned the transmitted code word because it turns out to be irrelevant. The residual error pattern is independent of the transmitted code word, and that is what actually permitted all of this analysis to be carried out. Okay. So, with that, that concludes our discussion on this topic, and now we are ready to start on talking about a new class of codes. This is also an important class of codes, and these go by the name convolutional codes. And the way I would actually like to do this is I am going to introduce an example convolutional code to you, and in fact the code that I will introduce to you is the prototype convolutional code, in the sense that if you open any book on convolutional codes, it is very likely that this is the example code that they will actually show you. It is a nice example code. So, we will take a look at this example code and we will proceed with it. So, we will actually study the encoder. Then we look at methods of representing the code symbols, then we look at something akin to something which is similar to the generator matrix, and so on. So, we will just keep pursuing this example. A little later I will come back and say, okay, but what is the general case, and the general case will turn out to be quite similar. Okay. So, here is our example encoder. In this encoder, the encoder looks something like this. So, you have a 2-bit, 2 registers like this, and what you have at the input is a stream of binary symbols, k going from 0 to infinity. So, this is a stream. So, let me do the writing later. Okay. I do not want to clutter the diagram. this is the input. There is a single stream of binary digits here, and at the output there are going to be two streams of binary digits, and these are generated as follows. Let me just clean that up a little bit. I think I can draw that better. So that is one output, and that corresponds to the stream VK1, and then there is a second output and again these are semi-infinite streams, meaning they start from 0 and go on to infinity. So, there is a stream of symbols coming in and there are two streams of symbols going out, and already you can see that there is a difference with block codes, because in the case of block codes you did not have these semi-infinite streams, because with block codes what you had was a fixed collection of message symbols and they were mapped to a fixed collection of code symbols. Okay, you did not have this infinite stream that is continuing. And also here we are starting off with the encoder. Okay, so what is the expression that corresponds to this? So, so what you are really saying here is that the first output is a function of the current input and it adds to the current input the immediate past two inputs. The second output adds to the current input the input two symbols ago. Okay. So, mathematically you would represent this like this. You would say that Vk1 is uk plus uk minus 1 plus uk minus 2, and then Vk2 is uk plus uk minus 2. So, this then describes the encoder. Now, convolutional codes belong to a class of codes which are known as tree codes. So, why are they called tree codes? Because you can actually represent each code word as corresponding to a path in a tree. So, let me draw the tree and try to make things clear that way. Okay. And so, what I am going to draw here are, let me also put some arrows on this. So, an up arrow means that the corresponding input symbol is 0, and a down arrow will mean that the corresponding input symbol is a 1. Okay. So, every code word trace corresponds to a path in this tree. And what about the output symbols? So, the output symbols are generated using this expression here. So, for that it is convenient to look at to perhaps set up a table So, let us draw a table in which we put down both inputs and outputs. So, here you have the input okay. So, this is your UK, this is what I will call the state of the convolutional code, and this is your output. Now, the state is really captured by the past two symbols. So, that is UK minus let us see UK minus 1, UK minus 2, and the output is VK1, VK2, right. So, this is what these things will represent. Now, let us look at the different possible states. So, you have 0 0 0 0, that is one state, then you have 0 1 0 1, you have 1 0 1 0, and you also have 1 1 1 1 and the input symbol can either be 0 or 1, 0 or 1, 0 or 1, 0 or 1. Now, the output, there are two outputs. So, one says that you add the sum of these three symbols. So, that is VK1, and so you add the 3. So, that is 0 1 1 0 1 0 0 1. Now, VK2, what it does is that, so if you want to see where I am getting that from, see VK1 adds the current symbol to the preceding two symbols, VK2 adds the current symbol to the symbol 2 symbols back. Okay. So, here is VK2 then. So, here I add the first and the last third entry. So, that is 0 1 1 0 0 1 1 and 0. So, these are your entries. Okay, so, now with that we can actually go ahead and put this down. Now, initially you assume, so each of these nodes here corresponds to a state. So, we assume the state is 0 0 here, and since you received a 0 here, it continued to be 0. This became 1 0. This became 0 0, this is 1 0, this is 0 1, and this one, this state here is 1 1. Okay. So, these in some sense are your states. All right. So, you have the states and you have your inputs, because whether it is an up arrow or a down arrow tells you what the inputs are, and from that you can actually proceed to write down what the corresponding outputs are, and you can check with that when the state is 0 0, the input is 0, your output is actually going to be 0 0, and that will continue here and it will continue here. But if your state is 0 0 and you actually get a 1, then it turns out that your output is going to be 1 1. Okay. and in similar manner you can actually fill in this entire tree. So, what this tells you is that convolutional codes are different from block codes in the sense that they can be represented as paths in a tree, and the reason why you introduce the tree is because after all it is a semi-infinite sequence. There is no notion of a block of message symbols and a block of code symbols. And then but convolutional codes, at least the class that are the class of tree codes we are interested in, are a little bit more restrictive than a complete general tree code, and the reason for that is because in a tree code you can have whatever rules for generating output that you want. It could be time varying, it could be nonlinear, but in the case of a convolutional code, convolutional codes are always generated by an encoder of this type. So, what is it that characterizes these encoders? Well, first of all, they are time invariant, that is, the output only depends upon the current and the immediately passed inputs. It does not depend upon the time. Okay, it does not matter whether it is morning or afternoon, the output is still the same. So, it is time invariant and then it is linear. Okay. So, in these ways it is a specialized tree code. So, this is just to put it in perspective. Okay, so, let us just put that down in writing. Convolutional codes belong to the class of tree code that are one of finite memory, two linear, and three time invariant. Okay. Now, if you want to do something analogous to what we did for the case of block codes, you could write down a generator matrix, except that it is not very convenient to write down the generator matrix because it would look something like this. So, here would be your input symbols U0, U1, U2, etc., and your output symbols, you could view them as being generated using a matrix of this type. So, it will be a semi-infinite generator matrix of this type, and this is what will lead to V 1 0, V 2 0, V 1 1, V 2 1, etc. Okay, so, this is, and you can check that this is true, because what we are really saying is, for example, take this symbol. We are saying that by the way, there is one thing I should clarify, that in this you always assume that this encoder, that the initial conditions are that both these registers are set equal to 0. So, may as well mention that. So, both are set to 0. So, both these registers are initially set to 0. So, that is your initial conditions. So, then you can actually verify that your output symbols are related to the input symbols like this, but this is not very convenient, again because it is semi-infinite. So, the more appropriate, so let me just call this the semi-infinite generator matrix. So, the more appropriate description of the code is in terms of polynomials and formal power series. Okay. So, we will make a slight detour and discuss the field of formal power series. So, in a way this will be a continuation of our earlier discussion, where we said that whenever we need some math, what I will do is I will actually make a slight detour, discuss the math and then bring you back to coding theory. So, when we were talking about codes, so I introduced groups, subgroups, cosets, rings and fields, okay, and vector spaces. So, similarly here it turns out that the math that you need in order to comfortably discuss convolutional codes is a little bit of algebra, and particularly you need to know what a polynomial is and what a formal power series is. So, the field of formal power series over F. F is also a field. So, in fact, just to make that clear, let me write this as over the scalar field F. So, this is the set of all terms of the type k is equal to minus d to infinity a k x to the k, where a k belongs to F and d is greater than or equal to 0. So, you look at this and say, well, isn't this a polynomial? And the answer is no, because first of all here you are permitting a finite number of negative coefficients and negative exponents. So, the x, you could have x to the minus 1, x to the minus 2 and so on, but you are only allowing a finite number of them, which is why you actually say k goes from negative d to infinity, where d is itself greater than or equal to 0. But and also polynomials have the notion of a degree, that is, there is a maximum exponent which you refer to as the degree, but here there is no maximum because it just keeps in general running off to infinity. Okay. So, in this way objects within the field of formal power series actually differ from polynomials. Now, how do you actually add and multiply and divide? Now, I am sure that any of you given a formal power series will know how to actually add and divide. Here I have used x as the indeterminate, but in our application to convolutional codes the indeterminate will be called d, where d stands for the delay operator. Okay. So, it is very clear how you would add two formal power series, because you just add them term by term. So, there is no confusion there. The question is, well, how do you multiply them? Well, again that is not, if you know how to multiply polynomials, I am sure you will figure out how to multiply formal power series. The only question is, how do you actually divide? Okay. So, I will, for that reason I will only illustrate division. Division, or rather, since we are talking about a field, what you really want to know is how do you compute inverses, because you really have in order to make something a field you need a set and you need two operations, addition and multiplication. So, the set is already defined here, and then addition I have told you follows in a very straightforward way, multiplication also. But when you go through the checking the axioms, the most puzzling axiom is probably the axiom of the multiplicative inverse. So, we will just illustrate that. So, it is clear that all field axioms are satisfied with the possible exception of the inverse. So, we will do this by example. Supposing you were to ask me what is d plus d cubed inverse. So, you will write this as d into 1 plus d squared inverse. Now, I just see that from my clock that I just have about 2 minutes to wind up. So, I think let me not pursue this example, we will do the computation next time. Perhaps I should spend my time just recapping. So, what we actually did was the first part of the lecture was concerned with standard array decoding, and we said let us actually use the standard array decoder and figure out how to carry out performance analysis by way of analyzing bit error probabilities, code word error probabilities. Then we moved to a completely new class of code known as convolutional codes, and I am giving you to begin with various descriptions of the code. Eventually, we will settle upon one or two which are convenient, but we are just introducing various descriptions, and we are somewhere in the middle, and we will continue next time by completing this discussion on formal path series. Okay. So, thank you.